This is the largest known structure in the entire universe, the Hercules-Corona Borealis Great Wall. It spans a staggering 10 billion light-years in length, 7.2 billion light-years in width, and 1 billion light-years in thickness. To put that in perspective, the observable universe has a diameter of 93 billion light-years. This structure alone accounts for more than 10% of that total range. Such a terrifying scale is enough to overturn everything we currently know about the cosmos. Modern cosmology relies on a core concept called the cosmological principle. It suggests that, on a large scale, the universe should be homogeneous and isotropic. In simpler terms, matter should be distributed roughly evenly. No matter which direction you look, the universe should look essentially the same. Currently, all cosmological research operates within this fundamental framework. By simulating the evolution of the universe, we can see a specific pattern emerge as our observation scale expands. Supercomputer models show that stars, galaxies, and other celestial bodies form a massive cosmic web. Every filament in this web represents a supercluster of galaxies. However, as the scale increases further, the distribution of matter is supposed to become increasingly uniform. Logically, a structure spanning 10 billion light-years, like the Hercules-Corona Borealis Great Wall, simply shouldn't exist. So, where did these measurements come from? With our current technology, observing objects more than 10 billion light-years away is incredibly difficult. We cannot see most of the galaxies within this Great Wall directly. We have to rely on indirect evidence. Specifically, it was identified through gamma-ray bursts, or GRBs. There are two main ways a gamma-ray burst is born. One is the explosion of a massive star at the end of its life. The other is a collision between two neutron stars. In either case, the event creates relativistic jets. These jets release intense gamma radiation. In astronomy, a jet refers to a stream of matter ejected at near light speed from the center of a celestial body like a black hole or a neutron star along its axis of rotation. To put it more poetically, a gamma-ray burst is the last scream of a dying star. According to the cosmological principle, stars should be evenly distributed throughout the universe. Therefore, the GRBs they produce should also be uniform. However, when scientists mapped the distances of these bursts, they found an anomaly. In a specific region of the northern sky, the distribution of GRBs was abnormally dense. This anomaly led scientists to conclude that a cosmic superstructure exists there, the Hercules-Corona Borealis Great Wall. Of course, some argue there might be other reasons for this cluster. Some scientists believe it could be a statistical error or a result of biased data selection. When astronomers analyze GRBs, they rely on data collected by telescopes. Like all scientific research, these observations have limitations in scale and range. If we assume matter is evenly distributed on a large scale, then theoretically, GRBs should be evenly distributed too. However, reality isn't always so ideal. For example, if GRB-producing bodies happen to concentrate in a specific area, perhaps near certain galaxies or black hole accretion disks, telescopes will detect more bursts there. This can create the illusion of an abnormal distribution, leading to the hypothesis of the Great Wall. It is also possible that other less studied regions contain many undetected GRBs. Our current telescope coverage is limited. We are far from having a uniform map of the entire universe. Therefore, this anomaly might just be a random effect caused by focusing too much on one area of the sky. Because of this, scientists today have become much more cautious and rigorous with GRB data analysis. On the 2nd of December 2023, a research paper titled Mapping the Universe with Gamma-ray Bursts was published on the preprint platform RxI. This study came from a research team at John von Neumann University in Hungary. They used data from 542 gamma-ray bursts. The spatial position and spectral redshift of each burst were precisely determined. Using a bootstrap method, they identified GRB clusters in both the northern and southern hemispheres, while avoiding the absorption effects of the Milky Way's disk. Previously, the redshift of the Hercules-Corona Borealis Great Wall was estimated to be between 1.6 and 2.1. Redshift, or Z, is a physical quantity that measures how much light has been stretched, allowing us to calculate cosmic distances. However, this latest data shows the GRB cluster forming the structure spans a much wider redshift range, from 0.33 to 2.43. This means the Hercules-Corona Borealis Great Wall might be even larger than we imagined. It might even be much closer to Earth than previously thought. In other words, scientists tried to prove it wasn't that big, only to find out it was much larger than expected. This is undoubtedly a heavy blow to current cosmological models. Perhaps we need to re-examine our fundamental understanding of cosmic structures. This discovery may only be the first step toward a deeper understanding of the nature of the universe. Currently, the radius of the observable universe is about 46.5 billion light-years. However, according to theories like cosmic inflation or the multiverse, the entire universe could be 10 million times larger than the part we can see. If that's the case, the diameter of the universe would reach a staggering 10 to the power of 23 light-years. At that scale, the Hercules-Corona Borealis Great Wall doesn't seem so exaggerated. It's like finding a single cherry in a jar of jam. It stands out. But if that jar were 100 kilometers wide, that same cherry would be almost invisible. Just like Einstein's theory of relativity, everything in the universe is relative. Our current understanding of the cosmic structure is still in its primitive stages. Only through relentless exploration and discovery can we get closer to the ultimate truth of the universe.